Hi there. In this video, we're going to discuss section 4.7, logarithmic scales. So what are logarithmic scales? These are scales that help describe situations in terms of easier numbers, such as single-digit numbers, and they also help us avoid large numbers and or negative exponents. So a lot of the scientists or mathematicians that came up with logarithmic scales they did it to try to avoid negative exponents or large numbers like things in the millions. For example, the Richter scale. When you talk about the size of earthquakes, it can be thousands, uh, 10,000s times larger, millions of times. And so instead of saying this earthquake is 800 million centimeters, we use the Richter scale. So we're going to talk about all that. And so the ones discussed in our book are the pH scale, the Richter scale for earthquakes, and the decibel scale for sound. So let's start with the pH scale. So the pH scale, what does this one do? So you may have already, if you're taking chemistry, you may have already heard about pH. But essentially the pH measures the acidity of substances. So some examples that I have are, for example, the pH of milk is 6.5. So let me handwrite that. So pH of milk is 6.5, while, for example, the pH of limes is 1.5 in the pH scale. So what does this mean? And so this discusses the acidity. So notice that limes, 1.5 acidity, that will mean it's very acidic, versus milk is not as acidic. And then the seawater, so if you take water from the ocean, the pH of seawater is about 8. So let me write that in as well. So pH of seawater is approximately 8. So you can see the level of acid in the substances. So limes are the more acidic. So the lower the pH, the more acidic the substance. The higher the pH, the less acidic. So think about when you go to the ocean and you swallow a big gulp of seawater, there's not much acid in that. So what is the pH scale? So the pH scale is equal to, or the pH is equal to the negative log base 10 of H plus, where H plus is the concentration of hydrogen ions. So H plus is the concentration of hydrogen ions in a substance. And hydrogen ions are very small, right? So usually you have, and that's where the negative exponents come in. So for example, if I wanted to know the number of hydrogen ions in milk, so let's take milk as our example. So find the number of hydrogen ions. So this is the H plus. So because the pH is 6.5, we're going to say then we're going to use the pH equals negative log of the number of hydrogen ions. So I'm going to have 6.5 is equal to negative log of H plus. And we're solving for H plus. We want another number of hydrogen ions. So when I do this, divide both sides by a negative, I'm going to have negative 6.5 equals log of H plus. And this is a log base 10. So to get rid of the log, use the definition of the logarithm, I have a log expression, so we want to write it back as an exponential. So then this will be 10 to the minus 6.5 is equal to H plus. So this is the number of hydrogen ions. So before this scale was created, people used to talk about the acidity of things by the number of hydrogen ions. So you will say milk has 10 to the negative 6.5 hydrogen ions. But using that kind of notation and language may be intimidating for non-scientists. And so the pH scale is something that allows it to be a little bit more easy to converse and talk about. The pH of milk is 6.5. Sounds better than saying the acidity of milk is 10 to the minus 6.5 hydrogen ions. So the next scale that we can talk about is the decibel scale. So the decibel, and you may have already heard some of these things, that you talk about the sound in terms of decibels. So the decibel scale measures loudness, taking into account the threshold of hearing. So oftentimes leaf blowers, things like that have a decibel scale. And so is the measure of loudness, taking into account the sensitivity of the ears and the threshold of hearing. And so the formula that is given in the book for this one is the decibel scale is B equals to 10 times the log base 10 of I over I naught. So where I is the intensity of the sound of an object, so like the leaf blower, or those hand dryers that they put in public bathrooms. And I naught, I sub 0, is the reference intensity of a barely audible sound. So this is kind of like your sound of reference. So reference intensity of a barely audible sound. So that one is based on the threshold of hearing. And so I naught has the number, this is 10 to the minus 12 watts per meter square. So this is a barely audible sound. And so just to give you an idea as well, so the decibel levels for certain sounds. So the threshold of hearing, threshold is 0. So the decibel level will be 0. And that's essentially the ratio of the intensity of an object. So it will be the same, I0 over I0. So it will be 10 to the minus 12 divided by 10 to the minus 12. So you get log of 1, and the log of 1 is 0. So that's the threshold of hearing. And then if you're just having a normal conversation, the decibel level is 50 decibels. So 50, and the decibel unit is usually lowercase d and uppercase B. So here I could change that to dB. I think your book has just B. And then a jackhammer. So if you hear a jackhammer, usually people are wearing those ear protection, because the decibel level of a jackhammer is 130 decibels. And so same as we did with the pH, we could find the intensity for a jackhammer by putting in 130 equals 10 log I over 10 to the minus 12, and then finding the intensity of the sound of the object. And the intensity of the sound will be watts per meter square as well. So let's do an example of this for what I was saying about the leaf blower. So say you have a leaf blower with an intensity of 3.2 10 to the minus 2. So the intensity of a leaf blower is 3.2 times 10 to the negative 2 watts per meter square. And so notice how this is a type of unit that may seem intimidating to work with. You're using scientific notation, so it may seem intimidating. And so the logarithmic scales allow us to talk about things in numbers that are easier to at least talk about. Zero, threshold of hearing is zero. A jackhammer has decibels of 130. And then there's usually something that tells you, okay, normal commutation 50 decibels. So anything higher than 50 is going to be loud. Anything lower than 50, right? If you're whispering, the decibels should be lower than 50. And so that's what you can hear. And so I'll be interested to know what are the decibels of those new hand dryers that they put in public bathrooms that I was saying, like those, what are they called, like accelerators. And I feel like I should be wearing earplugs when I use one of those hand dryers. So I choose not to use them because I value my hearing. Okay, so back to this. The intensity of the sound of a leaf blower is 3.2 times 10 to the minus 2 watts per meter square. So find the decibel level. So our equation is B is equal to 10 times the log base 10 of the intensity of the object divided by the reference intensity. So we plug what we know. So we know this is going to be 10 times the log base 10 of I is 3.2 times 10 to the negative 2 divided by I naught. So the reference intensity is 10 to the minus 12. So I'm going to put that in here. And because this is written like this in scientific notation, so I'm going to write 10 to the 12 is 1.0 times 10 to the negative 12, just to kind of make it look like they're both scientific notation. I could also just use rules of logarithms if I wanted to separate it, right? This, I can say that the laws of logarithms will allow me to say log of I minus log of I naught. And then notice that log of I naught would be log of 10 to the minus 12, which will just be equal to negative 12. Because the property of logs says if the bases are the same, you just get the exponent. But I'm going to choose to do it this way. And because then I can use scientific notation. So this will be equal to 10 times the log base 10 of 3.2 divided by 1 is just 3.2. And then I have 10 to the minus 2 divided by 10 to the minus 12. So I can subtract the exponent. So minus 2 minus a minus 12 becomes plus 12. So this is 10 times 10 to the 10, right? Negative 2 plus 12. And now I can put that in our calculator. And so putting that in the calculator, right, that's 3.2. So put the whole thing. If you have just a regular scientific calculator, you might have the key that has the double E, and that's the scientific notation. So you will do 3.2 E to the 10th, or you can just put in the whole thing, 3.2. You can use times 10 to the 10, and that will give you the answer. And so I get 105.05. And so we can say that then the intensity of a leaf blower, or the decibel level of a leaf blower, is 105 decibels. So compare that to the threshold of hearing in a normal conversation. So threshold of hearing is 0 decibels. Normal conversation is 50 decibels. So a jackhammer is 130 decibels, and a leaf blower is about 105. So when is it that you need to start wearing ear protection for sounds? And so that comes from the decibels. So 105, if you see people using leaf blowers, they usually have some sort of ear protection depending on the level of intensity of said leaf blower. So the next scale is the Richter scale, the one with magnitude of an earthquake. So we're going to look at that, but I am going to record a new video for that.